It's great to see so many faces of people that I know in the audience. I'll be talking today about astrobiology, merged beam studies that we've done at Columbia University. And this is funding that we've gotten from the National Science Foundation. According to the clock here, I have 5 seconds left, so I will speak quick. Great. Okay, here's an outline of my presentation. Actually, are you going to reset that? So you're going to set the clock so I know how much time I have left? Thank you. Great. I'll talk about the motivation. I'll describe the experiment. I'll talk about our results. I'll explain how we convert our experimental results into thermal data that the astrochemists need, and I'll give some brief conclusions. So, motivation. Why are we doing this? We want to understand the pathway from individual atoms in space to life on Earth and possibly other planets. And this is a picture of a dark, dense molecular cloud. It's blocking out the light, the stars behind it. Dark clouds like this are the birthplaces for stars. And from the material left over in the formation of a star, you get a planetary disk that forms. And molecules that were formed in that molecular cloud can be delivered to the new surfaces of these planets by meteors and comets, for instance, leading potentially to life. And we want to understand how far interstellar chemistry took us on this pathway. So molecular clouds have a very rich chemistry. Over 180 molecules have been found to date. 3/4 of these contain carbon, which is really amazing when you think about it. I've highlighted those here in green. Interstellar chemistry is organic chemistry. It makes me wish I had taken Orgo when I was in college. There's also the precursors to water, and I've highlighted those molecules here in blue. So the question arises as to where these molecules are formed. Are they formed in the gas phase? Are they formed on grain surfaces, or are they formed in ices? And astrochemists put together models to figure this out. Gas phase models, for instance, have about 500 species in them. They have about 7,000 reactions, but the rate coefficients for many of these reactions are poorly known. In many cases, they're just guesses, and often the networks are incomplete. So there's a lot of room for improvement. Gas, grain, and ice models are even more complicated because they have to take the gas phase chemistry, and on top of that, they have to include surface chemistry. But we don't really know what the surface structures are. They also have to include ice chemistry, but we don't really know what the ice mixtures in space are. We can make guesses for both of these. We also don't have a quantified understanding of the reaction rates on surfaces or in ices. So it's just plain hard. And the state of the field is that astrochemists make an observation and they determine a molecular abundance. They compare that to the model predictions from gas phase chemistry. If the models and the observations are in agreement, we think we understand how that molecule formed. If there's disagreement, it could be that the molecule formed on surfaces, it could be that the molecule formed in ices, or it could be that the gas phase chemistry is wrong. And what we're trying to do is improve the gas phase chemistry to better constrain where these molecules are formed. I'll be here a while, so I've brought a lot of water. So here's some of the gas phase pathways for forming the chemicals needed for life. This is a highly simplified chemical network to just highlight some of the key parts of it. Dense molecular clouds are primarily H2 with trace amounts of other elements such as carbon and oxygen. Cosmic rays, which are typically relativistic protons, zip through the cloud, ionize the H2, making H2+. H2+ reacts with H2, it gives you H3+. H3+ drives a lot of chemistry in molecular clouds. It likes to give up its extra proton, it's an acid. For instance, it can react with carbon, and it can make hydrocarbon ions. These are the first organic molecules in space. Sorry, I left that out. From there, these hydrocarbon ions can react with other atoms in atomic or molecular form, leading to complex organic molecules, such as carboxy, that's COOH, cyano, CN, and amino, which is NH. My group has focused on this link in this highly simplified chemical network. We also can make water. Again, that starts with H3+, reacting now with oxygen. It makes OH+, H2O+. These in turn react with H2 or electrons, and they ultimately form water. My group has looked at the oxygen on H3+ reaction. So these are some of the first steps towards forming complex organic molecules, towards forming water, and potentially towards us. So how well do we understand this chemistry? Here's a plot of the published rate coefficients for carbon on H3+, making CH+. Sorry, I'm getting over a cold. Fortunately, most of you have socialized medicine, so if you catch it, you've got health coverage. This is a plot of the thermal rate coefficient as a function of gas temperature. This is the cloud temperature that we need to worry about. It's 10 to 300 Kelvin. This horizontal line is the classical Langevin rate coefficient. These dashed curves are two different semi-classical calculations. They take the quantum mechanical potential energy surfaces, they run classical trajectories across them. They differ by a factor of 2 because of different potential energy surfaces. I want to emphasize and make this as a challenge to the theorists in the audience. Quantum mechanical calculations for 4-atom systems like this are beyond current theoretical capabilities. Go to it, guys and gals. Do calculations, please, we need them. There's one measurement by Dieter Gerlich's group. I'll describe it in a couple of slides. It was on H3+, but it was at a reaction temperature of 1,000 Kelvin. Well, molecular clouds are 10 to 300 Kelvin, so that's not the right temperature regime. So we really don't know before we did our measurements. We didn't know if the rate coefficient was up here, if it was down here, or if there was a steep temperature dependence. So, let me describe the experiment that we built to study this process. But first I'm going to explain why there are so few laboratory measurements for reactions between ions and neutral carbon. And the bottom line is basically that atomic carbon is highly reactive. And because of that, it's very difficult to make intense, well-defined beams of carbon. Only 2 approaches have been used to date. I only have time to talk about one of them, and I'll talk about the measurement by Dieter Gerlich's group. They used graphite rods, which they heated up to create basically a beam of soot. C, C2, and C3. Here's their schematic. This is their source. These are the graphite rods that they heated up. The soot, which was C, C2, C3, flowed into a cold trap containing H3+. They had an unknown density of carbon. They had an unknown fraction. They also had a kinetic temperature of 1,000 degrees. One of the advantages of their technique, though, is because the H3 plus is formed in the cold trap. The internal energy of the H3 plus is only about 77 Kelvin. I'll come back to this point later in the presentation. So, as I said, there have only been 2 approaches that have been used to date. It's clear that a complementary technique is called for to advance our understanding of carbon chemistry. So, here are some of the advantages of the approach that we've developed. We can generate a beam of pure ground term atomic carbon. I'll explain how. Because the beam energy, we're using KeV beam energies, so the beam energy is well defined. Because we use fast beams, means that we can use standard techniques for measuring the density profiles and determining the overlap between the 2 beams. Here's a picture of the apparatus. This is in a basement lab with no windows. We're astrophysicists, we pretend to see stars anyway. This is our sputter source that we use to make C- and O-. We extract our anion beam. We direct it towards the interaction region. Before it gets to the interaction region, we have a nearly 2 kilowatt infrared laser, which we shoot across the anion beam. And we convert about 2 to 4% of the anions to neutral carbon or oxygen. We get rid of the anions, and we're left with a neutral beam that continues ballistically into our interaction region. We have a second ion source here to make H3+. We extract the H3+, we merge it with the neutral beam. Both beams are moving fast in the laboratory, but because they co-propagate, the relative velocity is very slow. And we can simulate reaction energies comparable to collision temperatures of 25 Kelvin. This is where the chemistry happens. At the end of the interaction region, we direct the daughter products, shown by this blue arc. We direct them into a channel electron multiplier. We count daughter products versus relative energy between the beams. I'd like to thank the team members, my group members, who did this work. Start out by thanking A. O'Connor, who's in the audience. He carried out the lion's share of the design and construction of the apparatus. He took the lead on the carbon chemistry. Eula Stutzel here was with me, and she took the lead on the hydrogen leg of the apparatus. Just about the time that we started to collect the carbon measurements, shortly before that, Natalie Derouet joined on. She's also in the audience, and she took the lead on the oxygen chemistry. Ken Miller here is the corporate memory in my laboratory, and he's been keeping it together for the last 6 years. And I'd also like to thank my longtime collaborator, Savin Urban. Besides being a great scientist to work with, he also keeps us well stocked in Belgian chocolate. I'd like to thank him for that. All right. How do we make the ground term atomic carbon? Here's a Grotrian diagram. C- is one of those rare atomic anions that has a ground term. It's the quartet S, and a tenuously attached metastable level. It's attached by only 40 millieV, so it's readily destroyed in the extraction voltages at our ion source. That gives us a pure beam of C- in the ground term. We use a laser, 808 nanometer, that's 1.5 eV per photon. And we photodetach into the ground term of the atomic carbon, into the triple P term. And based on work by others, we expect to statistically populate the triple P term. And it's similar for oxygen, except there's no metastable level in oxygen. Here's a little bit more about the carbon fine structure levels. At a temperature of 1 Kelvin, the J=0 level is entirely populated. As you get to molecular cloud temperatures, 10 to 300 Kelvin, first the J=1 starts to get populated, and then the J=2 gets populated, and when you get to higher temperatures, the J=2 level dominates. And at the highest temperature shown here, you basically reach what we call statistical equilibrium. Later I'll discuss how we use this temperature dependence to convert our results to thermal rate coefficients. The ion source produces internally hot H3+. H3+ is formed by proton transfer, H2+ on H2, just like cosmic rays in molecular clouds produced H2+ on H2. They lead to H3+. At least one of these parents has to be vibrationally excited, so it produces an excited H3+. And there are theoretical and experimental results that indicate the internal energies are between half and 1 eV. So that corresponds, based on theoretical partition functions, internal temperatures of about 2200 to 3400 K. We'll discuss later why this is not an issue. But I do want to point out that there's work going on. My former postdoc, Holger Krakow, is principal investigator on producing a neutral beam for the cryogenic storage ring in Heidelberg, Germany. My other former postdoc is first author on a poster on Friday about this work, and that's also being done in collaboration with Savin. So I encourage everyone to go check that poster out. Results. This is the merged beam's rate coefficient. That's the cross-section times the relative velocity convolved with the energy spread of the experiment. It's not a thermal rate coefficient, not yet. This is as a function of relative energy. The black data points are for forming CH+, the red are for forming OH+. The error bars are the one-sigma counting statistics. And the solid line is not a theoretical calculation, it's an empirical fit to the data. And we see that as the relative energy increases, the merged beams, I also want to emphasize we can get down to temperatures of about 25 Kelvin. So as the relative energy increases, we see that the merged beam's rate coefficient increases. We attribute that to new vibrational and rotational levels opening up with additional collision energy. At some point, both channels turn off as competitive channels open up. And the first of these to open up is X on H2 plus, giving you X plus H plus H2. Station identification. Break. Okay. We have results for forming CH2 plus and OH2 plus. Both of these decrease with increasing energy. We attribute that to the decreasing time for the intermediate complex to rearrange itself as the collision energy increases. Let's focus on the carbon results. These are the merged beams results for both CH plus and CH2 plus. The vertical solid lines show the thresholds for the competing channels to open up for internally cold H3 plus. The dot dash curve shows where our fit appears to turn over. That suggests that the H3 plus is internally excited by about 0.63 eV. Using the theoretical partition function, that implies an internal temperature of about 2500 Kelvin. Again, we don't think this is an issue, as I'll explain shortly. So thermal data. Now we have to take our results and convert them into a rate coefficient for the astrochemists. First, we generate kinetic temperature rate coefficients. We've measured sigma times V, averaged over the experimental energy spread, F sub EX. We know this energy spread from the beam shapes, from the trajectory geometries, and from the source energy spreads. So that means that we can extract the cross-section. We then convolve the cross-section with the maximum ultimate energy distribution to generate a temperature rate coefficient. I'm calling it kinetic temperature because we have not yet corrected for the internal energies of the colliding systems. So we generate this kinetic temperature rate coefficient, and now we have to correct for the internal populations of the colliding systems. Here's the carbon on H3 plus pathway. And in order to make this correction, we do the same thing that state-of-the-art theory does for their calculations. We use the adiabatic approximation, and we connect the entrance, intermediate, and exit channels. So we have carbon in various fine structure levels, triplet P2, 1, and 0. We couple these with the H3 plus to form various J and M sub J states. And then we further couple this to CH3 plus. I should actually say the theorists did this work, I did not. And the CH3 plus has 3 different symmetries that play a role. The triplet B2 is attractive, and that leads to CH plus and CH2 plus. The triplet B1 is also attractive, that leads to CH plus. The triplet A2 is repulsive and does not participate in the reaction. So what we do is we use the temperature dependence for the carbon fine structure levels to determine the temperature dependence for these intermediate states. And I'm going to skip the algebraic corrections that we do, but we can use that to correct our experimental results and generate thermal rate coefficients. Sorry. So these are the derived thermal rate coefficients for carbon on H3 plus. The black solid line shows our CH plus results. The gray error band is the experimental uncertainty. This is thermal rate coefficient as a function of temperature. I'm showing the range relevant for molecular clouds in yellow. These triangles with the error bars are the experimental results from Dieter-Gerlich's group at 1,000 Kelvin. We see really good agreement. I want to point out, they had internally cold H3 plus, we have internally hot. So within the mutual error bars of the 2 experiments, it appears that the internal excitation of the H3 plus is not important. Is the classical Langevin rate coefficient. If you scale that to take into account the change in fine structure populations in the carbon, here's what you get. And these are the 2 semi-classical calculations. And I want to point out that we see really poor agreement between theory and experiment in both the temperature dependence and the magnitude for forming CH+. In blue, we've shown experimental results for forming CH2+. The blue band shows our error bar. The tracked results are shown by the triangle. Good agreement again. These are the semi-classical results. We get reasonable temperature dependence agreement, but it's off by a factor of 25 to 50 in magnitude. We also have results for oxygen. In this case, I've summed the results, so this is the rate coefficient for forming both OH plus and H2O plus. I left that off the Q graph. Our results are shown by the black line. The gray error band is the experimental uncertainty. Here's the temperature range relevant for molecular clouds. The triangles are 2 different flowing afterglow measurements at 300 Kelvin. To within the mutual experimental error bars, we see really good agreement. Yet again, implying that the internal excitation of the H3 plus is not important for this chemical reaction. This is the Langevin rate coefficient. We only see good agreement at the lowest temperatures. This is the scale Langevin rate coefficient, where we scale for the change in quantum fine structure levels of the oxygen. We see reasonable agreement at higher temperatures. These are the semi-classical results. These 2 dashed, and you can't really see their dotted curves. The temperature dependence is reasonable, but it's off by a factor of 1.4 to 1.7 in the magnitude. So that brings me to my conclusions. We've developed a new apparatus to study astrochemical reactions with atomic carbon and oxygen. We've measured carbon on H2 plus. These results have just been published in the Astrophysical Journal Supplemental Series. The reference is given up here. We have measured oxygen on H3 plus. Those results we're writing them up right now. Fully quantum mechanical calculations are clearly needed for these systems, for astrochemistry. So come on guys, theorists, scals, any gender in the audience, anyone who wants to calculate these systems, please go to it. We're currently investigating the astrochemical implications of our results, and I'd like to stop there and thank you all for your attention.